All right, so earlier we talked about Newton's laws. Newton's first law is that an object in motion stays in motion and an object at rest stays at rest unless acted on by another force. Newton's second law relates force equals mass times acceleration, understanding that net force always determines the direction of acceleration. And Newton's third law is for every action, there is an equal and opposite reaction. Um, Understanding that that's happening on two different objects, right? The action happens on one object, the reaction happens on another object. And then we started talking about free body diagrams. So a free body diagram oftentimes will draw just a box, and then we'll show the different forces acting on it in different directions. Or we might, instead of a box, we might draw some sort of dot in order to make it happen. So those are free body diagrams. They just represent an object and all of the forces acting on it. We also started talking about splitting up the sum of forces in the x and the y direction. So instead of F equals ma, we have the sum of forces in the x direction equals the mass of the object times acceleration in the x direction. And the sum of forces in the y direction equals mass times acceleration in the y direction. So we have to remember to split things up, and we also have to remember to sum all of the forces before we solve for things like mass. So we also talked a little bit about the types of forces. So if this is my object, right, this point is my object, we have gravitational force, which is always downwards or towards the center of the earth, and that's our weight, right? So our weight is equal to mass times gravity. If we're talking about this as a force, a lot of times we'll make this gravity, the 9.81, we'll make it a negative, because a lot of times we assume that up is positive. But when we're talking about the weight of something, just in general, a lot of times we just take the magnitude of that weight. You wouldn't say I weigh negative 900 newtons or whatever it is. You would just say I weigh 900 newtons. So we talked about weight. We also talked about something called a normal force. So a normal force is something that pushes up perpendicular to the object. This would be a normal force. And a lot of times in our textbook, our forces will also have the vectors on top of them, to indicate that they do have a direction. But normal force is perpendicular to the surface of contact. Okay, so if I have something sitting on a table, the normal force is pushing up perpendicular to that surface of contact. We also talked a little bit about how weight and mass are not the same. Mass is the amount of matter that makes up an object, and weight is the gravitational pull. Your weight will be different on different planets, in different places. Your mass will always stay the same. We also talked a little bit about apparent weight. If you've ridden an elevator, you notice that you sometimes feel heavier than normal when the elevator starts moving, and then you feel lighter than normal when it comes to a stop. And so that comes directly from Newton's second law. So if you think about your weight experience, you're experiencing the force exerted upward on your feet by the floor. If the floor exerts a force greater than your weight, you feel heavy. So if the floor exerts a normal force on you that is greater, so this is you normally, right? Your weight and the normal force balance each other out. But when an elevator starts moving, this force becomes greater. So you feel like you weigh more. And then when the elevator slows down, it becomes less because there's less of an acceleration in the downward direction. So that is apparent weight. Sometimes things feel like they weigh more because there's something else causing additional acceleration in addition to what gravity is. So now today we're going to talk a little bit about springs. So if I have a spring here that's hanging from a surface, it's not a great spring, but this is my spring. When it is totally at rest with nothing on it, this is called my equilibrium length right here. This is harder than writing upside down on a whiteboard. Holy moly. So this is my equilibrium length when my spring is totally at rest. But what happens when we attach a weight to this spring? We all know what happens. The spring stretches out. And so I'm going to call the distance that it additionally stretches right here. This is going to be my x. That's the distance that my spring changes. So when springs have a force exerted on them, let's say by like a weight, then it stretches a length of x. When we double the weight, so if this is our weight, if we have 2w, we actually end up doubling our x. So if this weight is 2w, this length here is 2x. So through experimentation, this guy with the last name Hooke figured out that the weight and the amount that the spring stretches are corollary. They correlate to each other. So this guy came up with a law to talk about how springs expand. So this is called Hooke's law, Hookes, Hooke's law. And he said that the force is equal to a spring constant, which we're going to call K, times the change in length, which is X. So force, spring constant, change in length. K is the spring constant, and we have units for the spring constant of newtons per meter. X is going to be in meters, and force is going to be in newtons, right? So this is Hooke's law. So now we're going to do a practice problem. A spring with a constant, so K, a spring constant, 21 newtons per meter, is stretched 3.4 centimeters. What force is required to cause this amount of stretch? So we're searching for force. So go ahead and pause the video, try it on your own, and then restart the video and we'll solve it together. Hopefully you paused the video and worked through it on your own. But my force is equal to Kx. We have K, and then I didn't tell you explicitly that this was X, but we said it had to stretch 3.4 centimeters. The thing that you'll notice here, hopefully you notice this, is we have centimeters here, but Hooke's law is in meters, so we have to convert the centimeters to meters. So my force is going to be equal to K, which is 21 newtons per meter. And then if I do centimeters to meters, I need to pull over twice because there's 100 centimeters in every meter. So this will be 0.034 meters. You'll notice that I have meters on the bottom, meters on the top, so those meters cancel out and give me units of newtons, which is exactly what I would want for a force. And so then I'll do 21 times 0.34, and my force is going to be equal to 0.71 newtons. That's my answer. So let's do one more practice problem. If I have a spring, again, this is a very terrible spring, but there's a force that pulls down on it of 1.2 newtons, and we have a stretch here of 6.4 centimeters. What is the spring constant for this spring? So we're trying to find K. Pause, try it on your own, and then come back and we'll solve it together. So we know that force equals Kx. My force is 1.2 meter or newtons equals K is what we're solving for. And then I have an X of 6.4 centimeters, but again, I have to convert that to meters. It's going to end up being 0.064 meters. Now I can solve for K. I can solve by dividing both sides by 0.064 meters. So then this cancels out on this side. Then I get 1.2 newtons divided by 0.64 meters. So my K is going to be equal to 19 newtons per meter. The last one that we have is I have a spring and I'm pulling down with a force of 2.3 newtons. My spring constant K is going to be 19 newtons per meter. When I pull down with this force of 2.3 newtons, what is my displacement? That would be my X value. What does my X equal? Find the answer in both meters and then convert to centimeters. Do this on your own.